In this video we're going to look at how to generate more efficient meshes, so using different element types and mesh types to generate a mesh with a lower node and element count. We will look at this for both CFD and stress analysis models. Firstly, we will look at the stress analysis example. So you can see lots of small fillets and radiuses as this CAD is designed for production. Likewise, on the bolts you can see radiuses and detail, and also here on this flange a large number of smoothed fillets. Firstly, we'll generate an automatic mesh. So this will be minimal user setup, and this will generate a mesh capturing all of those small features and fillets. So we're going to use a proximity-based meshing method. So this will look for small gaps, parallel surfaces, and we specified the number of cells within this gap to 2, so we can adequately capture any of the thin walls within the model. And from those settings we can then automatically generate the mesh. By default, the meshing algorithms pick different mesh methods based on the geometry. So wherever possible it will generate a hex or swept mesh and tetrahedrals in the more complicated regions. So you can see the duct here at the side is hex. So with the default settings you can see that you capture all of the detail. It generates a good quality mesh, but maybe not that efficient, so a large number of nodes and elements due to all of these small features and fillets within the model. We will now take a cut plane through the model to visualize the volume cells. This is a good way to visually validate the proximity-based size function. So we requested a minimum of 2 cells through the wall thickness, which you can see that we have achieved. Finally, we will look at the node and cell counts or element counts using the automated mesh methods. So in the statistics you can see that the number of elements is in the order of 505,000 and the number of nodes 856,000, and we will come back to these numbers later. Now we will go back to the geometry and look at how we can remove some of these small features to generate a more efficient mesh. The geometry tools within ANSYS make it very easy to be able to select surfaces and extend to their neighbours. So we can select one fillet surface, extend, and use the face delete command to heal the geometry. So with just a few clicks we can simplify those large numbers of fillets to a very simple shape that will result in a more efficient mesh. We can also look at it on the flange region. So again, a large number of fillets, select one, extend, face delete, and the geometry is automatically simplified. You can also do this one by one, so more interactive picking, and again it's very straightforward to make a more efficient geometry. So we will be able to mesh this section with fewer elements later. You can also select multiple surfaces together. So in this case we've got a large number of fillets. Again, just select one of each, extend, and then you can remove them all in a single step. We can also do the same for the bolt heads. So removing this, we'll be able to use a different mesh method later to generate a hexahedral mesh in this region. And finally, we can look at adding information instead of removing information. So where we have this pocket, we can generate a fill volume. So we simply select the surfaces that describe the volume. So the lower face and the surrounding surfaces. And then we can generate a new volume within inside this region. and then this new volume can be combined to the existing volume with a Boolean operation. So simply select the two volumes, Boolean, and use unite. And you can now see that the pocket has been removed from the model. Now we will go back to meshing and see how these changes influence the node and element count. A powerful feature of the ANSYS tools are that they are persistent, so all of the initial mesh settings are remembered even though we've changed the geometry. So we're going to use a different mesh method here on the bolts. We're going to choose multi-zone, which allows us to generate a hexahedral mesh automatically. And now that those fillets are removed, it's very straightforward to generate a hex mesh. We will keep all of the other settings the same, so proximity-based meshing, with exactly the same parameters that we used before. And then we will generate a new mesh. With the persistence of the meshing with inside ANSYS, it's very easy to remove a feature, regenerate the mesh, and see what effect this has. So here is our resulting mesh. You can see much more efficient use of cells in these regions. Again, so we really have radically reduced the node count in these areas with a heavy amount of fillets. And also you can see a hexahedral mesh generated for the bolt. We can now look at how this affects the statistics. So we now have 399,000 elements. Now let's look at the same case for a CFD simulation. So now we were looking at the fluid domain, so this is the inside or the inverse of the solid model. You can see a large number of small ducts here which could produce a very inefficient mesh using tetrahedrals. So we're going to start in a similar way to the stress analysis model, using minimal user setup and using the automatic methods. In this case, we're going to mesh with proximity and curvature, so this will detect small fillets, especially those small ducts within inside the model. We specify minimum and maximum sizes as well as a growth ratio. To generate a good quality mesh for CFD purposes, we also want to create an inflation layer to adequately capture the boundary. The ANSYS meshing tools provide an automatic way of doing this. It will automatically inflate surfaces in selections that you don't name. So in this case, we can very easily select inlets and outlets in the model, which we will later use within the solver. And the automatic inflation will inflate every other surface in the model apart from those named selections. We can also specify some individual sizes on some of the larger areas of the model. We can now generate an automatic tetrahedral mesh with boundary layer inflation. The boundary layer inflation tool also can reduce the overall inflation height in small areas, so it can automatically reduce the total height in each of the small individual ducts and then expand the inflation layer height in the larger free stream areas. So you can see the inflation on the outlet, and there are two inlets to this model. Here's the first inlet, and finally the inflation on the second inlet. So you can see that it generates a very high quality tetrahedral and prismatic inflated model with very minimal user input. If we take a slice plane, you can also see how the inflation layer varies in height depending on local element size and geometry features. So you can see the smaller offset where you have the smaller tetrahedrals. If we now look at the statistics for this automatic method, you can see that the number of elements is in the order of 2 million. We will now look how you can make a different mesh using some more interactive tools. So this model has been cut into different meshable sections, so areas that could be generated automatically with hexahedral cells. So you can see this cylinder has been segmented from the initial model. We can use a sweep method and an edge inflation. This area will be modelled with tetrahedrals and have a standard inflation, and this will be swept with an inflation from a surface. So this decomposition may only take a few moments and will allow you to generate a much more efficient mesh. The mesh generation tool will generate tetrahedrals and inflation layers where specified and swept meshes, and will also combine them to make them node consistent. So this will be one continuous mesh with multiple mesh methods all used at the same time. So you can now see the resulting mesh. You can see a large number of hexahedral elements due to the decomposition of the model. Again, if we look at the outlet, you can see the inflation layer as well as the swept mesh method. And on the first inlet, again, you can see a continual inflation layer, and also on the other inlet. And most importantly, all of those small ducts of the model are now generated with hexahedral cells, so much more efficient use of cells. And you can see how the mesh transitions perfectly from tetrahedral to hexahedral, and every node is conformal with inside the model. If we look at the statistics, you can see that the number of elements now is in the order of about 1.4 million. So to finish off, we will now look at a comparison. So you can see in the stress analysis example that we have a node reduction in the order of 23% and a cell reduction in the order of 27%. And in the CFD example, you can see a 23% reduction in nodes and a 39% reduction in cell count. These reductions are very useful if you wish to consider optimization as part of your design process, or you're looking at getting your results faster.